to look at the data from two perspectives. One, perhaps, look, there's a racial discrimination element. That's what Munnell et al. 1996 were looking at when they set up the original HMDA data set. They had 2,381 loan applicants, and they reviewed then lending decision on the basis of not just race, but some of these other important factors that the individual's credit score or debt to income ratio, or did they have a public bad credit record, so on, right? And another reason why we're interested in this is it also provides us with a way of understanding how algorithms work and how algorithm lending might be automated, right? So if you think of in recent years, we see, Revolut has come in, and they are definitely a disruptor in the financial space. If we look at Robinhood, in terms of the stock trading and so on, if you look at Stripe in terms of payments, there's a lot of innovation taking place. And although the mortgage activity is a traditional banking activity, it may well be that some of this activity finds its way into individuals using these type of apps, or the new plumbing involved in the financial system, right? But maybe make use of the apps for mortgages. I mean, if you have a credit card and can borrow money through credit card facility, what's how, and if you leave a trace, a data trail in terms of your purchases and so on, it may well be possible that the Revoluts and so on could automate some of this mortgage type lending activity. Now, how might that work? Well, one way of understanding it is to look at the cTree here that comes from Varian 2014 Big Data New Tricks for Econometrics paper in the Journal of Economic Perspectives. He sets out the code that allows us to run this. Now I have the code below, and the code implements cTrees, Logit models, and RandomForests. So I'm going to take a snippet here of the code. So this is code that I took directly from the paper, right, from Varian's 2014 paper. Again, in this instance, what I'm going to do is I'm going to go into our studio. Now I have below a Colab where all that code is set up. The issue with the Colab is it can be a little bit clunky loading in some of the R libraries, right? So while that's there and while it all works reasonably well, right, and there's no issues other than the cTree actually is a little bit squashed. Okay, so some of the graphing in the Colab for some of these R packages is not completely optimized, as you can see, right? There is a little bit of latency when you're loading up some of the libraries. So a good idea here is to just go into our studio, right? And I'll open it up, our studio, open up the app, the desktop app, and then I have it here. And we load in file, new, R script, Control V, and all our code has gone in, right? So it's basically code from Big Data New Tricks for Econometrics from the Journal of Economic Perspectives, and that was 2014, and it's Varian. So first thing we need to do here is load in the party library. So that's what makes available the cTree, right, and the conditional inference tree. Now in our studio, if you want to see if you have a particular package available, right, you just type in to see is it already preloaded onto your machine. If it wasn't, right, if let's say we didn't have party available, I would just come here to install, and then I would I'd enter in party, and it would find it. Now there's party and party kit. I think party kit is a newer iteration, but we'll use party just to be consistent with Varian. And I would just put in party and then install. and it takes about a minute or two to install that, and then we make it available in our environment here. Likewise, the ECDAT, right, which we have here, that's a package, an R package, which is just basically a data package. Okay, so we have it there. Now you can take a look at these and drill down a little bit, but it's just, there's loads and loads of data available here. So there's this description of the data. There's 4,654 observations, and it's just quite a neat little thing there. R seems to have a lot of these type of packages, right? There's a diamond data set. There is number of observations 308. It's a cross section from 2000, and it just has data relating to diamonds. And you see that a lot, in fact, in a lot of the tutorials and so on online. Computers, cracker, consumption, doctor. Okay, so just very interesting data, and it's there and it's handy to have. So we're going to load that in and make it available in our environment. So that's what's going to bring in the HMDA data. And then to make that available in our global environment, right, we just do data HDMA, right? Now we need to fix the data a little bit, because in the, as you might have seen before, condominium is a term that's used in the data set. Hal says he doesn't like it, fix the annoying spelling error. And he does that. If we take a look now, instead of condominium being written, that's been changed to condo, right? Otherwise, you have all the debt to income ratio, the household expenses to income, the loan to value ratio, the credit score, the mortgage credit score, the public bad credit record. It's a binary. You either have you have a finding against you, you're tarnished somehow. Maybe you owe government taxes, denied mortgage insurance, right? Self-employed or not, are you married? So single, yes. Unemployment rate in your profession, so the applicant's profession. Are you buying a condominium or not? So that's a 1-0. Black here denotes African American or Latino. So no means you're part of the bigger majority of people, but yes would mean that you're part of that minority of African American and Latinos. And then deny, did you get the mortgage? So deny no means you got the mortgage, you were approved, but deny yes means you didn't get the mortgage. Okay, so that's our basic data, and there's 2,381 observations. Now we can set a seed. Sometimes you need to set a seed if you're doing random forest and you want to replicate what you did before. So that's something you put in maybe early on. And then like what we did before, we want to get all the complete cases. If you look actually at the data, it turns out that the very final one, there's a couple of missing cells. So to just eliminate that applicant, right, we put in the syntax, look, we just want the complete cases, no rows where there's empty cells or data missing. So we call that all. We create a new object. It'll appear up here, the global environment, and it's called all, right? So you can see now we're down to 2,380, and that last applicant, right, they're no longer to be seen, right? They're gone. Okay, so that just cleans it up and makes it a little bit easier to work with. Now, the first thing we're going to do here is run the cTree, right? And the cTree is a conditional inference tree. And basically it's just saying, look, take deny and predict, did you get the mortgage or not? And then regress that or model that using all, each of the data, each of the columns in our data set, right? So if we go back to all for a second, we have all these columns there. If you like, you might call them attributes or features, and you're going to use each of these to predict the deny, right? So it's, again, it's a nice shorthand. Look, model this, target this by using all the data, using all the columns, right? Now all, in this instance, just refers to the object all, right? But when I when I say, look, use each column here that's being denoted by the squiggle. And then if you want to plot it out, it's simple enough syntax, right? Plot the object all fit, and to get a good view of that, come over here to zoom, and you can see that now we can get better by making it go full screen, and we get an economic sort of analysis here. Now, there's a couple of reasons why this is interesting. It's interesting from the perspective of the original Munnell et al. 1996 paper, right, where they were trying to address themes of racial discrimination, right, which was published in the American Economic Review, right? So quite a substantial journal. But when we look at our cTree here, there's another reason why this type of analysis is very interesting, and that is it provides us with a way of saying, how do we create an algorithm that actually arrives at a decision in terms of whether an individual should be approved for a mortgage or not. Now, what's not in that is this actually a healthy approach, right? So could we improve the algorithm that we pick out the worst credit risks, exclude those, and perhaps save some money for the bank, and pick out the good credit risks and lend to those individuals so that the bank remains profitable and the right side of the law, which is also very important, right? But if we try to read this cTree, what it's revealing is, look, in terms of whether you got the mortgage or not, at the bottom here, we have what we might refer to as leaves or buckets. And the buckets are saying, look, yes means denied, no means not denied, it means approved, right? So if you were successful in not being denied mortgage insurance, that means being approved mortgage insurance, and your credit score was lower than 3, the credit score went from 1 to 6, and your debt to income ratio, so your debt service to income ratio was less than 43, and you had, you're even better, your credit score was 1, can't be less than 1, right? So 1, then what we're finding is out of the 2,380 applicants, we're looking at 1,272 here. Most of those overwhelmingly were approved their mortgage. And then on the other side, if you look at those who were denied mortgage insurance, most of those, I think with the exception of 4, they were unsuccessful in getting a mortgage. Yes, they were denied a mortgage more than, I'd say, 90% here. So I think it was 44 out of the 48 were actually denied mortgage. There was 4 exceptions. Okay, if you were approved mortgage insurance, which you typically need, and your credit score was greater than 3, and you had no public bad credit record, and you had your loan to value was small, well, less than 95. Now, 95 is actually quite a high level of LVR. When we looked at this descriptive statistics, we saw LVR, the mean LVR loan to value rate is about 77%, 75, 77, that range. But if you're lower than 95% and you are lower debt service to income ratio lower than 41, and you're part of the majority, so not black, right, then less than 10%, I would say, here were excluded who were denied mortgage. However, if you were African American or Latino, then that went from being less than 10% to above 21, 22% denial. So there is some difference there, but Varian describes that as being marginal. But overall, when you look at this, what you have is a schema that describes a means by which to frame an algorithm, right? And that algorithm then could be used to automate decision lending processes, right, or mortgage lending. Or it could be if, let's say, you excluded the variable race so that the algorithm was blind or naive to race, and you otherwise applied this analysis, the cTree analysis, and you felt that by and large, this behaviors or set of behaviors that were captured in the cTree basically captured good sound lending practice, then any other decision in future may be made by a human being in terms of whether they approved their mortgage or not could be flagged if, let's say, an individual with very good credit quality, with very strong credit quality credit scores, mortgage credit scores, no public bad credit record, debt service to income, so on, quite low. If those individuals were denied mortgage, maybe this is an algorithm that could flag difficulties with the underwriting process, right? So there's a number of different ways we could find this type of approach interesting, not just purely in trying to uncover was there racial discrimination, but just also generally in terms of how you'd go about automating a lending function, which increasingly has become, it's going to be quite standard, right? We can imagine, given the extent to which the disruptors have arrived and there's a lot of financial innovation, and I think it's a great fear of banks at the moment, the traditional banks, the pillar banks, if you like, that because most young people rely heavily on their apps for their banking, that they may, as a first port of call, go to an app to apply for a mortgage rather than go to a bank, right? Okay, let's look at some of the additional analysis then, right? Now, one of the things we would like to do if we were developing an algorithm like this is to see to what extent the algorithm was actually accurate, right? So there is some issues with what we have here. A lot of the time we're not predicting. There is some error, right? When you look at this, we would say, okay, this group who satisfied these conditions seem to get their mortgage approved, but there was a small slither who were mislabeled, perhaps, right? So embedded in this, naturally, there are, we never have a completely, or we don't appear to have in any instance, in any leaf, any bucket, a clear-cut case that everybody was approved or everybody was denied, right? And so if your model is producing these type of outcomes, inherently there is error, right? You could call it mislabeling, and maybe it isn't error, right? That's also something, maybe something else has been taken into account, not captured with the statistics, right? And for these purposes, when evaluating a model like this, we would like to look at the instances where the model predicts a certain outcome that's different from the actual outcome. So if you take this all fit that we've generated, this is an object that has been created. It's the model, it's the cTree algorithm. And with that cTree algorithm, we can predict the outcomes. So we can take our data and predict the outcomes from the data. We can take the model, take the original data, plug it back into the cTree model, the all-fit model, and then predict what the actual outcome should be. We would call that a new object, all predict, right? Which appears here. And then we can say, look, we would like to tabulate the all deny. If we take the all deny, it's just it is just the outcomes, the actual outcomes in terms of each individual, were they approved, were they denied, right? So when we looked at the HMDA data, let's go back into our data for just a moment, right? The all $ deny is basically this column of data. All $ deny is just that data right here at the end, right? So that's what we're pulling out onto the console. When I print this out, when I run that, that's what we have here, right? Now we want to compare that against the all predict, right? And the all predict, we generated how? Well, we used the model. We used the cTree model, and we predict out what the actual outcomes based on what? Based on if we had fed into the algorithm this raw data, right? So if we excluded the last one, fed in here this raw data, what does the all fit predict? it predicts the all predict, and that's these outcomes. Now, what we want to do is to tabulate and compare all predict against the all deny, and then create what's known as a confusion matrix. And let's print that out and see what we get. Okay, so we have this in the console, then we have this confusion matrix. Okay, now to understand that this is a kind of okay, so we have here the all.conf that's coming out of the cTree modeling. The tabulation that I've put here, that's up on the portal, right? So basically we're looking at the output from the confusion matrix. We've tabulated it with using this table. And if we want to interpret our results, then what we observe is that there was 117. So if we can compare the quadrants, right, with the true positive, the false positive, the true negative, and the false negative. So the first one we might take a look at here are the true positives. So these are the individuals who were actually both predicted to be denied their mortgage, but actually were denied mortgage. So the model cTree is predicting you were denied mortgage, and the reality is that individual is denied mortgage. Then on this other, on the true negative quadrant here, we have 2035. Now, most people were approved for mortgages, right? And the model here is predicting this 2035 who were predicted to be approved their mortgage, but actually were approved mortgage, right? So you have that combination, predicted to be approved mortgage and actually approved mortgage. Then we have the false positive here, the 60. And if you like, the error that we're getting in terms of our modeling then is the 60 and the 168. And when we look at that, the 60 here denotes what? The 60 here are the false positives, predicted to be denied mortgage, but actually approved mortgage. Right, so you're predicted, the model is predicting that the mortgage was denied, but actually you got the mortgage, right? And then on the 168 that we have here, that's a false negative. And if you like, that implies then that those 168 from the cTree confusion matrix that we just tabulated, they are predicted to be approved mortgage, but actually were denied. Right, so it was predicted. The model was predicted. You would have been approved mortgage, but you're actually you were denied. So there is some degree of error here that we can see, and the error is being captured here in the off diagonals. There's more error predicting those who were denied, as we can see, right, than being approved. So we're quite good at predicting. The cTree is predicting reasonably well those who were approved for mortgage, but then we can see there's some margin of error here when we're predicting those who were denied mortgages. Okay, now we can take those numbers and just look at the, you know, if we take the overall the 60, let's do this very quickly. If we took the 60 and we added in the 168, and then we divided that in turn by the 4, so that in fact it's 2,380, but let's just add them, 2035 plus we have the 117, and then plus the error then, so that'll bring us up to the total and the 168. And if we run that, okay, we get a measure of the amount of error. So there is this degree of error here in our prediction, right? That just under 10% of the prediction was wrong. Okay, so okay. Take the all conf to 1 and 1, 2, and estimate, add those together, and then estimate the amount of error. The all error, if you like, here, the 228 that the cTree model is producing, right, is coming from what? It's coming from, if you take 60 and add 168, that's the mislabeling, you get 228. So out of the 2,380 applicants, we are, with the cTree model, we are we're predicting badly, or we're erroneous in predicting 228, right? Okay, that's a measure how well the model is doing. Okay, now, again, going back to the original Munnell et al. Paper, the issue arose in terms of whether an individual, if their race or ethnic affiliation somehow was influencing the lending outcome, right? Were you being denied or not? So Halvarin, again using the code, our code from Halvarin, what he, the next step here is he says, look, let's take our data set. Let's take all again, right? Which is everything here. And column 12 is black. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one is the column relating to black. Let's exclude that from the analysis, right? So let's take that and exclude it from the analysis and say, look, our data set is no black. And then let's take and we can have a look at that no black data set. You can see we have everything like what we had before as with all, but we've removed the 12th column relating to the ethnic affiliation of the individual, the ethnic grouping of the individual. So we rerun the cTree, exclude African American and Latino column, and see, but they're still in our data set, just we haven't we haven't signaled in the data the individual's race. And we produce, again, in the very same way, a cTree, right? The no black fit, and we can graph that if we so wish. We could take take the plot all fit like what we've done before. So copy, come down here and Control V and plot, and we could plot in black fit or no black fit. No black fit. Okay, so we've run this, right? And then we can just take a look here and we get a new graph. And let's zoom in and take a look at that. Now it's excluded. Let's zoom. Now zoom is already open, must be. So we close down. Yeah, this is the new cTree. It has removed any reference to race. And again, we have some similar type conclusions. So this is the new cTree, the new algorithm running without race being incorporated into the analysis, right? And what we're finding is that the, again, pretty much very similar type of output, but just we're missing the reference here to race on this side of the cTree. So in the branches and in the nodes as we come down, far down here where we had a reference to ethnic group, that no longer pertains. And we look at it and it seems to have a kind of similar fit, right? Okay, now how good is this model? Is there deterioration in the model? Well, we can, like before when we did predicted our model outcomes, we can do that again here. Maybe if I remove, copy, cut and paste that, Control V, put that underneath, and then run no black predict. So this basically is predicting, again, what does that mean? It's gone into our global environment. We can Control V. Let's just run that C. It's just, again, predictions based on the cTree that excluded from the schema any reference to race. Now, as a quick check, right, we can compare, we could see, is there any difference between the original model output in the original algorithm that included a reference to African American and Latino ethnic grouping, or excluded it? Okay, so we can compare both set of predictions, and to see to what extent are there differences. So a quick check is to see, are they all equal? And when we run that, we find both outcomes, even when we exclude the variable here for race, right? It makes no change in the model predictions. And Varian looks at that, and his interpretation of this is basically, his interpretation is race is not important. Using this analysis and differing from the original findings of Munnell et al., Varian asserts here, look, this is evidence to suggest that race is not a critical determinant in deciding whether an individual is approved for a mortgage or not. Okay, so that's a kind of an interesting output, right? From just parsing through our analysis and considering race. It would appear at first glance, looking at this, maybe it's not such a significant variable. Now, there's other reasons why we might suspect that it is, and Varian actually touches upon those, because he says race might be correlated with something else. But just purely in terms of including it in our data set and working through the cTrees, where we have two cTrees and compare the outputs where one has race, one excludes race, there's no differences in model predictions. Okay, so that's a powerful assertion, right? Okay. In this section here, which I'm just following, so what we've done so far, we've loaded in the party packages and made them available in this environment. Party, we have the HDMA, we removed one of the rows. We changed condominium to condo. Again, this is all following religiously Varian. We've run a cTree that's coming out of the party package that we made available here, party, and ECDAT that's giving us the HMDA data set. We've run the cTrees, we've estimated confusion matrix. With that confusion matrix, when we look at the output, we're getting a kind of reasonably good type of output. Now there is some error, right? That's the off diagonals here. And a lot of the time we're predicting people are going to be denied a mortgage. In reality, that's not true. So we're predicting 168, we're getting them the mortgage. We were, you know, and the reality was something else. So we're getting we're getting quite a bit of error here, right? But again, that's just the nature of the beast. The framework, the rules that people are using are not consistent. Remember, each lending decision was probably a different type of personnel, a different day, a different interaction. So consistency in terms of setting out an algorithm cannot be ensured, and inevitably there is going to be error here. That would be, even if we had a fairly strong set of protocols that applied, I'm sure, or a stringent set of measures in terms of how to allocate credit, I'm sure that is something that would be just inherent in this type of analysis. Okay, so next area that was looked at, we ran the cTree with and without reference to ethnic groups. There was no difference in the prediction of the model. That would suggest that race may not be a hugely important variable. That's at variance with Munnell et al. 1996. We then, when we ran that little snippet of code, basically said, look, is there any differences? Are they the same? And the cTree without reference to race and with reference to race made exactly the same predictions. So they were all the same. Now what we could do is set up a loop. This is what is set out by Varian. He sets up a loop and he says, look, run the cTree, and in each instance, sequentially drop one of the columns, drop the column step by step. So you have a set of columns here in the all data. And he says, look, just drop this column, this one, this one, this one, this one, this one, and do it sequentially. And each time run a cTree and just see what the effect is in terms of, do you get an increase in the amount of error, right? So obviously some of the factors here, some of the columns are going to be important in, you know, making predictions. Race, he finds, may not be overwhelmingly important. In fact, when we exclude it, didn't seem to have much, it made no difference to the overall predictions of the model. So he says, go back again and in each instance, exclude one of the variables and then predict, was the individual denied mortgage approval or not, right? So again, this is a series of cTrees. Now what has popped out here? So basically 12 cTrees are estimated, and sequentially we've dropped each column step by step. And then what we've done is we have estimated the increase. So we looked at the amount of error in each cTree, and then we subtracted that error from the all error from the original baseline model. The baseline model is where we have everything, right? The all error, if you recall, when we estimated all error before, we had all error. When we estimate that, there's 228 in the baseline model. That came from the confusion matrix that we just saw a moment ago, right? There's, if you add the 60 and the 168 from the baseline model, you get 228. Now, what if you drop each column and look at how much error that contributes, right? So as you run through the loop, that at the end, you estimate the error in each of these new models, these new cTrees, and you subtract the old baseline error. Now, typically, you're going to get a higher level of error if you drop a column. If you have less data, your model is going to be less accurate. With the debt to income ratio, when we dropped that, we had 2 additional errors, right? When the household expense to income ratio was dropped, we had no additional increase in error. LVR, however, is very significant here. When we dropped LVR, we had 6 additional errors coming from the cTree. When we dropped the credit score, we had 8 additional errors. When we dropped the mortgage credit scores, no additional errors compared to the baseline model. When we dropped the public bad credit record, we had 12 additional errors. So that looks like quite a significant variable. When we dropped the denied mortgage insurance, right? And we can understand that when we looked here, denied mortgage insurance, a lot of the time here, that is quite a strong variable, right? If you're denied mortgage insurance, most of those guys didn't get mortgage insurance. When we dropped that, we got 36 errors. When we dropped persons, are you self-employed or not? No effect on error. If you're a couple or not, no effect in terms of the amount of prediction errors. Unemployment, condominium, and race. So these variables here that have zeros, we would suspect are not that significant. According to the cTree algorithm, they're not the most, they don't have, at the margin, they're not having any effect on the amount of error we get from the cTree model. DMI, very important. Public bad credit record, important. Credit score, important. Loan to value ratio, somewhat important, and DIR, marginally important. We wouldn't exclude it. Okay, so that's a kind of a rich way, very nice way of going back and using the cTree algorithm and just reproducing another tree in each instance, and then comparing the error to the new model against the baseline model. Again, it's a way of plucking, it's a way of seeing how important are these variables, right? It's a way of determining how important are each of those. Right, we come back. Okay, so we just looked at the cTrees, and then when we had, this is again Hal Varian's code, and he had set up cTree models. He had established a baseline model. He examined the amount of error, and then he excluded different variables, including the variable making reference to race. It seemed to have no impact on the overall error of the model. When we compared the baseline model error to when we excluded race, there was no difference in model predictions. He then did that for each of the columns of data, right? So each of the variables in the all data, when you exclude each of these sequentially, right, some have more impact than others, and we were able to trace that out. The most important one was denied mortgage insurance, and then public bad credit record. Okay, next bit then of that script, our script that HAL Varian 2014 provides us with is the Logit model. And he says, look, let's fit a Logit model. And this is quite a standard model. It's a standard model in econometric analysis and time series analysis. But in econometrics, when we have qualitative or binary outcomes, we tend to rely upon the Logit model a lot. It's available in R. So we initially, again, as before, we take the deny column here where you approved mortgage. So deny no means you were approved. Deny yes means you were denied your mortgage. And then you regress that and all the other variables. So this squiggle, empty, and then dot implies everything, all the columns in the data are going to be used. So we run that and we call that Logit fit. And then using the Logit fit model, again, we're not actually providing you with a summary here of there's no equation here that we've provided. Okay, we could do it, but we haven't made it explicit. We just like take that Logit fit and say it's a black box, and we're going to predict the output. We're going to predict the model output based on the data set that we have been using. So we're going to predict the Logit fit, and we have Logit temp, right? And we could take, I suppose, a look at Logit temp, right? Logit .temp, it's gone into our global environment. Let's just take a look at it. And what you see is a series of what? It's a series of predictions, but they're probability predictions, right? So for the 2,380 applicants here, we've gone through them sequentially. And you see, to predict, what it's doing is it's giving us a Logit model fit, which is bounded between 0 and 1, right? So you're not getting a 0, 1 prediction. You're getting a probability estimate as the output here. And then what we would do is then say, okay, try to determine, are any of these greater than 0.5? And if they are, then that's consistent with, because you can see the bulk of them actually are low probability of mortgage being denied, right? So we're going to create a variable then that in the event, is it true that we are greater, is this Logit fit greater than 0.5? And if it is, then we would say that's indicative that there is, that strong probability is indicative that the mortgage is rejected, right? So the mortgage is denied. And we can take a look again at the Logit. Let's see how that then transforms that object. It's gone into the local environment. Let's see what Logit PRD looks like. And a series of true and false, right? But you will find the odd true one here denoting, look, there's an issue then predicting the mortgage is denied. And then we want to compare the all deny against the Logit predict and tabulate it, and then output a confusion matrix, right? And when we output a confusion matrix, this is what we get. And it's instructive to compare this confusion matrix against the one we used before in the baseline model. I think that was all fit or all conf, right? So this is the Logit model, and we've outputted a confusion matrix. Now, if you recall, what's the confusion matrix? I'll just go back. Okay, so we have outputted then a confusion matrix from our Logit model, and so what we observe here is perhaps a slight improvement on what we had seen before. So maybe just to make the quick comparison, if we go back to the previous confusion matrix that we had generated from the old tree, and that's just all conf, right? So it's this one here. So let's just run that to make the comparison, and let's just integrate in then the confusion matrix set up in the portal. Okay, so from the Logit model, what we're finding then is we had generated the true and false basically from the Logit model if the value had exceeded 0.05. Then we were saying that, look, it's true, the individuals denied the mortgage. So the numbers that we're getting here for the Logit prediction is, as opposed to the cTree, we have 266 true negatives. That means predicted to be approved, the mortgage, and actually approved mortgage. So both the prediction and the actual aligned. And then we have the true positive quadrant, 89 here, the true positives, right? So, and that's outlining predicted to be denied mortgage and actually denied. So if you like, these two values together, what they represent is where the model has predicted correctly. But then off diagonal, we have mislabeled, right? So basically here with the false positive, the 29 here represents a false positive, and we're predicted to be denied mortgage but actually approved. And then we have the 196 here, which we consider the false negative, where we're predicted to be approved mortgage but actually denied the mortgage. Now we can see, looking at this, we can estimate some of the error that's in there, but it's fairly clear looking at this that the Logit model actually is quite good in respect of predicting those who would have been approved a mortgage. So we have 266, but it's less good then at predicting maybe those who were denied mortgage. So that's the downside with our Logit model. cTree did a better job predicting here, but then we lost out a bit here. And we've more error than in the off diagonals with the cTree model. We have a little bit more error here. We have, if we add, that's 228 as opposed to 225. Just to recap then, we had looked at previously the cTrees. We had generated sequentially estimates of the performance of the cTree and how important each variable was in terms of predicting if the mortgage was denied or not. And we did that in a way that was quite clever, right? Again, we're using Varian's code. He drops sequentially each of the variables so that as we go through, we're dropping, you know, all a debt service to income ratio, and then we drop HIR, the household expense to income ratio, and the loan to value, and the credit score and the mortgage credit score. So we do that individually, and then we're looking at the overall performance of the model. And then that produced then for us in when we ran that estimation, that produced for us then the sequence, right, of how, and again, it's kind of a register how significant each of the variables are. And, you know, when we drop DMI, we're getting an additional 36 errors in our model performance, right? So that means it's falling when we looked at the all-conf, right, which is the baseline model. We had 228 errors in the baseline model. When we dropped DIR, we got an additional 2. And when we dropped DMI, we got an additional 36. So that's looks to be a very important variable. Then we'd moved the analysis to look at the Logit model, right? Like what we had done before, right? And when we run the Logit model, there is again using all, right? We use all these variables to predict an I, right? And then that gets, we take the Logit fit, which is the new object that is created here, and right, that then if we were to eyeball that for a moment, what we would see is a series of probabilities, right? Because the way the Logit model works, it's the model fit that you get is a fit that's not quite zeros and ones. It's actually a series of probabilities. The probit model produces output, right, that is a probability measure. And then you might want to change that or transform that into a kind of a binary output. And you might say the cutoff here is if the probability is greater than 0.5, then we're going to take that as a vote that the individual, it's true, they were denied mortgage insurance. But if it's less than 0.5, then we're going to say they were approved for mortgage, not mortgage insurance, for the mortgage being granted. Okay, so this new Logit predict model, if we print that off, we get these outcomes, and they're binary. It's based on, so we took the probability measures and we said, look, if it's greater than 0.5, right, then it's true. So the top one here, the top few are values that are close to 0, well below 0.5 if I recall. So if I go toggle back true, take a look, these ones here, the first row that we have, they're all way less than 0.5. Now below, when we look, we'll see for the, when we convert these values to true and false, they will all come up as being false. In other words, that the individuals were approved for mortgages, right? The individuals were approved. By and large, people were approved for their mortgages. The minority were rejected for mortgages. But as we go down through here, what we'll find is that first row here that we had, all false, meaning they were approved for mortgage, right? So that's the model prediction. And then we want to compare the model prediction, right, against the actual, right? So before we had all deny, and we want to compare this against the model prediction, and then generate a confusion matrix. Okay, and then we want to output that confusion matrix. And what we have then is we're predicting, look, 89. If you want to read this confusion matrix, what does it mean? It means we had assumed here that the model predicts 89 were denied mortgages, and the actual reality is 89 were denied mortgages. So of those who predicted, there was 89 who were predicted to have been denied mortgages, but it was actually true. And then here we have, using the Logit model, 2,066 were predicted to have been accepted who got mortgage approval, and that was actually true, that they were approved for mortgage approval. Otherwise, on the diagonals here, we have error. It's like it's mislabeling, right? In terms of the model. So this is the amount of error that we have. And if we were to just estimate, we took the 29 plus the 196, right? we get 225, and that's less than the 228 we had in the cTree. So the Logit model here is doing better. Again, more systematically then, if I take the off diagonals add together and then estimate the Logit error, it's 225, right? That's what we're getting. And that's better than the cTree model, the baseline cTree model, which was 228. Okay. So the Logit model actually is quite good. Now, if you wanted a summary, again, I think we might say, look, maybe we want an equation. And yeah, we can output that, you know, using the summary here. But sometimes with a random forest or whatever, it doesn't really make sense to try to get that equation. It's better to leave it as a black box, right? And just save it as a job, save it as a job lib. Okay, the next area we're going to look at then is the random forest, right? We had seen this before, but now we're going to make it available in this environment. Now we better check in our studio here, do we have that random forest package installed? If we didn't have, right, now it's there and it's ticked, that's grand. But if we didn't have that there, then we just put into the search engine random forest and it'll bring up, put an F there, capital F, and you can see it's there. And we would just install the package, the relevant package, right? So we don't have to install again, it seems to be there. So we can run it, right? And okay, so we set a seed. Now, typically you set a seed with a random forest because it's actually randomly sampling what it basically does, it runs a sort of decision tree, but it takes subsamples of the data and it's kind of cutting columns and cutting rows and then predicting mortgage approved, mortgage denied, right? And then it's taking the best fit. So basically what happens is this additional randomness actually helps in improving accuracy, right? And so it's kind of surprising, although it looks quite crude, this random sampling of the data and estimating and so on actually turns out to be quite good at giving us quite decent models. Okay, so we do what we did before. Before we had cTree and we had Logit, we're trying to predict deny, and then we're using all the data, all the columns. We run that, that's the name of our model. Then you might notice it's taking a little bit while to run this because random forest is a little bit more demanding in terms of processing power. Then we take the model and we're going to predict the output. So we take all the raw data and then generate a model prediction. We'll call it random forest predict. And that creates a new object in our global environment. And then we do what we did before. We'll tabulate, right? We will tabulate the error here. So we'll compare all deny, which are the actual mortgage approval denial, against the model predictions. And then we will report out what that confusion matrix is. And we're getting, like what we got before, confusion matrix where we have 2061 who were approved, the model predicts they're approved and actually approved. And then we have 94 who are, the model predicts were denied and were actually denied. And then the other bits are the error in our model. And what we don't seem to have success at is predicting well. We predict quite well those who are approved for mortgage. We have good accuracy. We don't have good accuracy those who are denied mortgages, right? So there's a lot of mislabeling would appear, but the model itself compares favorably. Again, if you take the 34 and you add on the 191, right? Maybe we should do it up here. Take the 34, right? So if we take our confusion matrix, take the 34 that we have here and add on the 191, right? The amount of error we have is 225. Now it was 228 for the cTree. It was 225 for the Logit model. The random forest is at least as good as the Logit model, right? The random forest model, a bit better than the cTree and a bit better than the Logit model. Okay. Okay, now we could have done that maybe using this approach, was a little bit more systematic. Again, the same results. So basically, we're adding the off diagonals, right, together and getting that 225. So that's what's going on here. And then a random forest allows us to identify the variables that are considered to be the most important, right? So we can do, again, we can look in the packages, random forest, and look for that var imp plot, right? So just come down here and get a little bit of information relating to what that provides us with. It's a dot chart of variables importance as measured by the random forest. Now, before we try to determine the variable importance, if you recall, with the cTree, we just dropped each variable sequentially. And that was one way of ordering which variables are the most important, right? So it would look like DMI, it would look like this public bad credit record, right? And then the other ones like black condo, unemployment single, and HIR, not that important. When we come down here and pull out this dot chart of variable importance, let's see, do we get, okay, so again, we're getting a little bit of, yeah, it's true. This DMI is seen as being important, but random forest attributes a lot more importance to DIR and HIR, right? And DMI is further down. The black variable is further down here and is also further down here. So again, I think the way Varian is reading this is, again, it's not that important. But what he does say in his paper is maybe the okay, so perhaps even though identified here just purely naively from the model as being less important, the variable that we have here for, or the attribute black, which denotes African American or Latino, I think Varian mentioned in the same paper, Big Data New Tricks for Econometrics, the Journal of Economic Perspectives, 2014, that doesn't exclude the possibility that this variable is highly correlated with the other attributes. So if we're looking at this feature or attribute and we're trying to predict whether a mortgage is approved or not, even though here the model is outputting that it's not so important, it could well be the case that the other variables that are hogging more of the explanation here are viewed as being more important in terms of predicting mortgage denied, mortgage approved, that this attribute may be correlated with the others. And if so, then we need a further discussion, a deeper discussion in terms of how significant race is. Okay, that's a kind of the overall, the Varian R code. So what we've done is gone through the R code snippet that was included in Varian's 2014 paper, Big Data, New Tricks for Econometrics. And it's a very nice way of, first of all, introducing machine learning. Secondly, it allows us to set up an algorithm, a machine learning algorithm that predicts loan approval. The data set that he introduces, the HMDA data set, it's an old data set that comes from Munnell et al. 1996, but it's a very nice, it's a pristine data set. It's a data set that actually in its time cost a lot of money to compile. I think tens of thousands of dollars, if not hundreds of thousands of dollars. And the Federal Reserve of Boston went to great lengths to get that data together. And it's nice to be able to use it here. It's also kind of a powerful way of demonstrating how machine learning works. I mean, when we plot out the cTree, for instance, it is an incredible way of, for the uninitiated, let's say, to understand perhaps how this process works. And even if we're not preoccupied with race here in terms of trying to figure out and it's very difficult, in fact, to figure out how embedded racism was here in terms of making available credit. But in terms of purely an algorithm and understanding, maybe trying to come to some kind of semblance of understanding in a systematic fashion how loans are approved, we have generated an algorithm from our data set. And one use here of this, one can imagine that in the fintech age, this type of analysis is extremely useful. Otherwise, I would say if we were to go a little bit deeper in terms of investigating race, one of the things that's not included in the original data set is the degree to which African Americans and Latinos, let's say, were approved for loans, but then also incurred higher interest costs, higher insurance costs. So again, maybe there were more African Americans proportionately who were approved with those higher loan to value ratios. But is there a possibility that, and we don't have that data here, including this data set, that they had to pay higher interest rates, that there was punitive interest rates applied? That data we don't have. And I think that is probably a fertile area to investigate in terms of trying to, it's an extra area that we should try to investigate to see if there is discrimination. Discrimination happens in different ways. One, obviously, the individual is excluded from getting mortgages. I mean, if you're just not accepted, if you're not approved, of course that could be obviously regarded as being discriminatory. But an even more sinister type of racism and discrimination would be you are approved for the loan, but then you are subjected to higher rates of interest, maybe disproportionately compared to the rest of the population. And we know from the early 1990s all the way through to 2007, increasingly, especially from 2000, there was a lot of predatory lending targeted at Latino populations, targeted at African American populations. Many people got mortgages, but were inappropriately given mortgages, given sometimes mortgages that everybody knew they couldn't afford. And that, even though there is lending taking place, it's a predatory type lending, and it's another form of discrimination that we should try to guard against. Okay, so that's it. I'm going to leave it there.